Hi everyone. Today I'll be going over alkanes, and I'm going to separate this sort of subject into three different categories. The first video, which is this one, I'll be going over alkane structure, how we draw them, and nomenclature. The second video, I'll be going over Newman's projections, and the third video, I'll be going over chair conformations, because I believe that each one of these subjects deserves their own video and their own lecture. So let's start out with the general alkane structure. So I've drawn sort of like an example here along with these other two. So recall when we're talking about alkanes, usually we'll be talking about them drawn in their line angle structure. Generally what a line angle structure means, it means that we draw the carbons in as sort of points. So each one of these points here, so this one on the end here, followed by this one, and so on, each one of these are carbons, okay? And each one of these carbons have enough hydrogens that are not drawn in to give it a full 4 bonds. So let's take this hydrogen as an example right here. It has 2 bonds on either side with 2 carbons. So that means it has to have 2 additional bonds with 2 hydrogens in order to give it 4 bonds total. And this will sort of occur with most carbons. So if we take another example, this carbon on the end here, this one has 1 carbon bond or 1 other bond. So it needs 3 hydrogen bonds that are not drawn in. So even though you don't see these hydrogens, even though they're sort of invisible, they are still present. They are just simply not drawn in. An exception to this, where the carbon will not have 4 full bonds, is if it has a positive charge, such as right here. Recall when we did formal charges that a carbon with 3 bonds and no lone pairs, if we do the calculation for its formal charge, carbon starts out with 4 valence electrons. It has 3 bonds here and 0 electrons in lone pairs. That means it has a charge of +1. So in this example, this carbon with the positive charge will only have a single hydrogen attached to it. Alternatively, if we have a carbon that has a lone pair, so let's say that this one has a negative charge right here, it'll have a lone pair because 4 minus 3 bonds minus 2 electrons and lone pairs equals a negative charge. So if you see charges like plus or minus on a carbon, that sort of tells us that the number of hydrogens that we would expect is slightly altered or changed. Okay, so here are a few examples. So how many carbons would this, or how many hydrogens would be attached to this carbon right here? I'll give you a second to think about it. It has 3 other bonds. So it has a single hydrogen bond right here. So that would be a CH, a carbon right in the middle there. All right. So this is just how I'll be drawing these things and how you should be familiar with the line angle structure and how to read them. If it helps, I would definitely recommend drawing in the different hydrogens, especially when we get into reactions like elimination reactions that actually have to do with those hydrogens, because that can help you understand what you're doing a lot better and therefore help you understand how this organic chemistry works. So there's another type of alkane. So up until this point, we've only been talking about alkanes that are sort of in chains. They're, whether or not like they're in weird shapes, they're all one chain. One end is not connected to another. Cycloalkanes, on the other hand, are sort of connected in a circle. That's why they're called cyclo. And you can see here the different shapes. If we have 3 carbons, 4 carbons, 5 carbons, and 6 carbons. And these cycloalkanes will be a little bit more important when we talk about something called ring strain and the chair conformation. But for right now, all you have to understand is that these exist along with those regular alkane chains that we were talking about earlier. Okay. Oops, didn't mean to do that. So let's continue on. So now we're going to be talking about nomenclature. Nomenclature is essentially just how we name these different alkanes. And the reason why we have these specific rules for nomenclature is to sort of be able to communicate what we are talking about to other organic chemists around the world. It's sort of the same idea as SI units, how every single society knows what a meter is or a second is because we've standardized that. This is the standardized naming protocol for alkanes. And what we will be doing is figuring out what the parent chain is first, Then we'll be finding any different functional groups that are present, finding the suffix, and then finding the prefix. So I always found that it was easier for me personally to understand what was going on if I did an example. So let's sort of skip over this real quick and we'll just go to one of the examples. Oh, and this is a good chart. This tells you what each different type of carbon compound will be called. Like, for example, if we only have one carbon, then it will be considered a meth, either a methane or a methyl group. Methane is if it's the parent chain, methyl is if it's a substituent, but we'll get into that in a second. I just want to get into this example here. So the way that I do this is my first step is find my parent chain. So find parent. And essentially what the parent chain is, it's the longest chain of continuous carbons on an alkane. This could be a cyclo. So like an example right here, this could be the parent chain, this one right here. It could just be a regular line, such as in this example, which we'll see in a second. It's just important to note that the parent chain cannot start on a line and end up in a circle. So like this whole thing, this is not one parent chain. The parent chain is either the cyclo, in this case, the cyclohexane, or the alkane, the linear alkane that's attached to it. Okay? So let's find this parent chain. So if I look here, I say 1, 2, 3, 4, 5. So my parent chain has 5 carbons. So I'm going to put that right here, 5 carbons. And if I look back at that table, I have this memorized, you may not yet. I see that the parent name or the base name for something with 5 carbons in it is pent. So remember that we're working with alkanes. So our parent chain is this long chain of 5 carbons that is an alkane. So we're going to end this parent chain with pentane. Okay? And so the next thing that I want to do is I want to find my substituents. So I'm going to put find subs. And so what I do there is I sort of highlight what is coming off of that parent chain. And in this case, it would be this guy right here. So I found my substituent. It is a 1 carbon substituent. Notice how I did not say it's 2 carbons, and that is because we start numbering on the carbon off of the parent chain. We do not include the carbon on the parent chain, which would be this guy right here, in the substituent name. So this one would have the base name of meth. Now substituents, at least alkane substituents, they'll have this base name, and then instead of ending with ane, we're going to end it with il, Y-L. So this substituent is a methyl. And so now I'm going to number the parent chain. Now the rules for numbering the parent chain is pretty simple. The carbons have to be numbered consecutively, but there is one rule that we have to sort of keep in mind. We want to number the parent chain so that we give each substituent the lowest number possible. So what I mean by that is looking at this chain right here, we see there are 2 possible ways to naming it. Putting a 1 on this end, making that my first carbon, or putting a 1 on this end, making the opposite carbon my first carbon. So what I like to do when I have chains like this, I like to number it both ways possible. So let's start with this top one where we have 1, 2, 3, 4, 5. And look at this bottom one, 1, 2, 3, 4, 5. So if we number it this top way, then we would give our methyl substituent the 4, or put it on the 4th carbon. If we number it on the bottom way, then we'd put it on the 2nd carbon, carbon 2. And putting it on the lowest carbon possible, or the lowest number carbon possible, is preferred. So instead of numbering it this top way, we are going to prefer the bottom way, where we make the rightmost carbon the first carbon. So now we're going to put that 2 in for the methyl. So now we have 2-methyl. And an important thing to note is that we put dashes in between letters and numbers. So you can see 2 and M, we put a dash between them, but we put commas between numbers and numbers. And I will show you what that means in a moment. I'm just going to finish up with this name first. So now we've numbered our parent chain, we've connected it to our substituent, and so now all I'm going to do is put my parent name at the end of it. So this guy would be named 2-methylpentane. And this tells us we have a pentane as our parent chain and a methyl on the second carbon. Okay? And so then that's how I like to name these different alkanes. Now, something that's important to note is what we focused on here was the prefix. When we're talking about the prefix, generally we'll be talking about different alkyl groups, which is just groups made up of only carbon, or we'll be talking about halogens. It's a little bit different when we get into functional groups because functional groups will change that suffix. So remember how we said that our parent chain is an alkane and we end it with ane? Sometimes that ane will change. So let's say that we have an alkene. Recall that an alkene has a double bond somewhere between two carbons. Instead of ending it with ane, we would end it with ene. So it's important to note that the substituents will cause the prefixes to change. So 2-methyl, 5-ethyl, that sort of thing. And different functional groups will cause the suffix to change. And we'll get into more about that when we get into those different functional groups more specifically, such as alcohols, alkenes, alkynes, and the like. So recall that I talked about how the different, recall how I said that if we have numbers next to each other, they'll be separated by commas. So let's say that instead of having this single methyl right here, I have 2 methyls. And so it's the same parent chain, same pentane, and it's going to be numbered the same way because 1, 2, 3, 4, 5. That's the first way that we're going to number it. It's the correct way, but I'm going to show you why right now. If we numbered it the other way, we would put our substituents on 3 and 4 rather than 2 and 3. Obviously, the 2 and 3 substituents will be lower, so we're going to prefer that way, okay? So now we have 2 methyl groups attached to our parent chain here. So instead of calling these methyl groups methyl, we're going to say dimethyl because we have 2 methyls. So this is a dimethylpentane now. And now we have to designate what number carbons these 2 methyls are on. So like I said before, these methyls are on 2 and 3. So we're going to say 2, 3 dash dimethylpentane. Okay? And so then that's what I mean by numbers are separated by commas and numbers and letters are separated by dashes. And notice here that the last substituent, or in this case, the only substituent, is going to be right up against the parent chain. Okay? Okay, so let's continue now. So let's talk about drawing the compounds. So this is sort of the same process that I did before. So the first thing I'm going to look for is the parent chain. In this case, pentane, same thing as before. So 1, 2, 3, 4, 5, and then I'm going to number it. In this case, it doesn't really matter which way we number it, just so that we number consistently because we are the ones drawing this compound instead of naming it. So 1, 2, 3, 4, 5. So our ethyl group is going to go on carbon 3. So it's going to go on this carbon right here. And an ethyl group, just a reminder, an ethyl group is a 2-carbon group. So I draw out from 3. Here's my first carbon. Here's my second carbon. And so then here is my 3-ethylpentane. Okay, so now let's scroll down one more time. Oops, that is not what I meant to do. Let's scroll down again. So 2, 2, 4, trimethylpentane. So we have 3 methyls on a pentane. So our parent chain here, pentane, 1, 2, 3, 4, 5, just like before. We number it 1, 2, 3, 4, 5. And notice here we have 2, 2. All this means is that we have 2 methyls on 2. Yes, I just said 2 a lot. So 2 here is going to have 1 methyl here and then 1 methyl here. Okay, so 2, 2. And then we have 1 last methyl on 4 right there. And so here is our 2, 2, 4 trimethylpentane. Okay, so now let's talk a little bit about cycloalkanes. So remember in the parent chain how we just said it was like the base name plus ane. So hexane would just look like this. So 1, 2, 3, 4, 5, 6. However, if this hexane is arranged in a cyclo, such as right here, where all we're going to do is simply add cyclo in front of it. So cyclohexane looks like this. Regular hexane looks like this. Okay? So it's pretty easy. And again, we're looking for the longest parent chain possible. And we're not sort of going around the cycle. Either the parent chain is the cyclo or it's not the cyclo. You can't have sort of parts and pieces of the cyclo as part of the parent chain. A good example of this would be sort of if I had, let's say I have a cyclohexane, and then I have a substituent coming off like this and a substituent coming off like this. I cannot say that my parent chain looks like this, because then that would be sort of bisecting the cyclo, which we can't have. Either our cyclo is our parent chain or it's not our parent chain. In this first case, it is our parent chain, because if we see here, we have 6 carbons within the cyclo, so 6 here, and then we have 1, 2, 3 in that chain outside of the cyclo. However, in this bottom one, we see we have 1, 2, 3, 4 carbons outside the cyclo, and then 3 carbons within the cyclo. Okay, so that makes our 4 group here the parent chain, and our 3 group here a substituent. So how do we name these things? So we're going to name them essentially the exact same way that we did before. We find the parent chain, in this case, cyclohexane, which we discussed a little bit before. And then our substituent is going to be this propyl group. So we have a propyl group as our substituent. And you may be wondering, how do I number this? Well, again, you want to give the substituents the lowest number possible. So we're going to start 1 right here, and then we can either number it clockwise or counterclockwise. So 1, 2, 3, 4, 5, 6. It doesn't matter which way we go because there are no other substituents. However, if there were substituents such as right here on 5, we want to number the other way in order to give that substituent the lowest number possible. Okay? So back to this. And so then we would say it's 1 propyl cyclohexane. Technically, for this one, you do not have to put the 1 here, because technically it's sort of implied, because again, we can number this hexane any way that we want, as long as it's consecutive. But here we're going to make it just 1 just for the sake of clarity. Sorry if you heard my cat there. He just completely ignored the sign I put up. He's very rude. Anyways, back to this guy right here. So we can see here, our parent chain is made up of 4 carbons. So that means our parent chain is going to be butane. And then we can see that if we number it, 1, 2, 3, 4, we have a cyclopropane, or a cyclopropyl rather, because it's a substituent, on 1. So I say this is 1 cyclopropyl. I hope I don't run out of room. 1 cyclopropyl butane. And notice here, we have to put the 1 here, because unlike with the cyclo here, we have to number it giving the end carbons either 1 or 4 in this case. We can't just start from the middle, like changing this 2 to a 1. So in this case, we have to put the 1. All right. Let's just continue on here. And so here are a few more examples. Try to do these on your own, and I will just pause the video if you need to, and then we'll walk through these together. So if we look here, we see we have our cyclo right here, and then our chain outside of our cyclo right here. Our cyclo is made up of 6 carbons, and the chain outside is made up of 1 carbon. So obviously the 6 carbon cyclo is going to be our parent chain. Recall, cyclohexane is our parent chain. We can see here that since this guy has 1 carbon in its substituent group, it's going to be a methyl group. And if we number this guy, 1, 2, 3, 4, 5, 6, we can see here that we have 1 methyl cyclohexane. All right? And so then that's how you would figure out that one. So let's go on to the next one. We see here that this cyclo is right here, and the chain outside is right here. So we can see that the chain outside has 1, 2, 3, 4, 5, 6 carbons attached to it. And we can see the cyclo has 4 carbons. So now our parent chain is going to be the alkyl chain outside of the cyclo. And again, this is going to be hexane. And then that means our substituent is going to be cyclobutyl. Okay, so the name for this guy, And if we number it, we can see it's going to be 1, or not 1 there, but 1, 2, 3, 4, 5, 6. And the reason why I didn't make this one 1 is because this one is already part of our substituent right here. If I make that one 1, it makes it a lot harder to tell what the parent chain is and to make sure everything is okay. So we can see here that this is the substituent. So I'm not going to put any substituent, I'm not going to put any carbon on that substituent in our parent chain. So we can see here that we have a 1 cyclobutylhexane. Okay, and that's about it for naming. There's one more thing I sort of want to go over really quickly before I wrap up here, and that's the different types or the special substituents that you may see. So I'm just going to make a parent chain right here, nice and long, just so I can show you. So when I'm talking about special substituents, I'm either talking about special substituents with propyl groups or special substituents talking about butyl groups. And if you don't have these memorized, it's fine. But propyl is 3 carbons and butyl is 4 carbons. So if I have just a regular propyl group, then I would have 1, 2, 3 carbons right here, okay? But a special type of propyl group called isopropyl will have the carbon that's attached to the parent chain be this second carbon right here. So isopropyl would look like this. It's still made up of 3 carbons. It's just attached in a different place. So it's sort of an isomer of a propyl group. So we call it isopropyl. Okay? Butyl works in a very similar way. So butyl is 4 carbons. So a regular butyl would look like 1, 2, 3, 4. So that's a regular butyl. But what if, similar to the isopropyl, we connect it to the second butyl right here instead of the first butyl? Then it would end up looking like this: 1, 2, 3, 4. And we can see that this carbon right here that the parent chain is attached to is a secondary carbon. So we're going to call this sec-butyl, because instead of being attached to that first carbon, we're attached to the secondary second carbon, so sec-butyl. Similarly, we can have something called tert-butyl, where instead of having the butyl being just a regular chain, as in just a regular butyl chain or a sec-butyl chain, all of the carbons are sort of attached to one central carbon right there. And that central carbon is a tertiary carbon. So we call this tert-butyl. Okay? And then there's one last type of butyl, one last sort of isomer of butyl, and that's called isobutyl. And it looks very similar to isopropyl, except it has an extra carbon connecting this forked bit right here. So we still have 4 carbons, which makes it a butyl, but instead of being just a regular butyl, it's known as an isobutyl. So these are all special names. And one more thing I want to go over before we end here: whenever you have multiple substituents on the same parent chain, we are going to order those substituents by alphabetical order. So I'm going to clear the screen. So let's say that we have a parent chain right here, and then we have a methyl group right here, and an ethyl group right here. So methyl group, 1 carbon, ethyl group, 2 carbons. And if we find the parent chain, we see it's 1, 2, 3, 4, 5, 6, 7, 8. This is octane. And if we number it, 1, 2, 3, 4, 5, 6, 7, 8, one way, and then the other way, 1, 2, 3, 4, 5, 6, 7, 8. Actually, instead of making this octane, let me make it a little bit more clear which way is the correct way of numbering. So I'm going to instead make this octane into a nonane. So a nonane, which is 9 carbons, right there. And then if I number the other way, 1, 2, 3, 4, 5, 6, 7, 8, 9. This top version of numbering is going to be preferred because we put our substituents on 4 and 5 instead of 5 and 6. So that means that we have a 4 methyl and a 5 ethyl. And so you may be wondering, what order do I put this in the name? Well, I'm not going to look at this number. And instead, I'm going to look at the alphabetical order here. So M and E. E obviously comes before M. So we're going to start with ethyl. So 5, ethyl, dash 4, dash methyl, nonane. Okay? And so then this alphabetical does not apply if we have, like, let's say that we have two methyl groups, then that would make it dimethyl. This di here does not affect the alphabetical order because it's not actually the name of the substituent. Rather, it's telling us how many of that substituent there are. Okay? And so then that was just the last thing I wanted to go over. So that was generally the overview for nomenclature. Next, I'm going to get into Newman projections, but again, I want to make that its own separate video so it's easier for you to find and it's easier for just me to reference back to it. So yes, if you have any additional questions, just let me know in the comments or send me a message.